In this video, we're going to learn how to evaluate our regression as a whole, how well it predicts, how well it fits our data. We're also going to look at how to evaluate our individual coefficients. Specifically, we're going to be looking at B1, right? That is the one that really defines the relationship between our two variables, so that's where we're going to focus. Before we get into that, I want us to talk a little bit about errors. We've talked about errors quite a few times in the past, and we're going to keep talking about them. So last class we calculated this regression equation, right? And we looked at how we can use that to predict our dependent variable, in this case number of hats owned, if we know our independent variable, right? If we know the age that we're interested in. Again, that's specific to this example. When we are predicting, right, unless all of the data that we don't have that we're trying to predict, unless all of it falls on that line, we're going to have some error, right? So we're going to have some error in our predictions, and we want to know that as we move forward, right? That's going to help us evaluate our predictions. It's going to help us evaluate our regression, right? What are the errors that we would expect to see in our prediction, right? The lower those are, the better, right? Just like in most cases when we're talking about errors. The lower the errors are, the better. So the main way that we're going to look at this is through the mean squared error. So here we've got mean squared error. We should be at least somewhat familiar with this concept after looking at ANOVA in chapter 12. We had mean squared error there. It was just the sum of squares error divided by the degrees of freedom. And that's exactly what's happening here as well, right? The sum of yi minus yi hat squared, that is the sum of squared errors, right? So observed minus predicted, that is the error. Square it, sum them all up, sum of squared errors. And then we're dividing by n minus 2, which are the degrees of freedom. All right, so the lower these are, the better, right? And we will be using these later on. And just for, so for our example, so for this regression, all right, we have a sum of squares error of 69.919. The next thing that we're going to look at is goodness of fit. This is one of the ways that we're going to evaluate the regression as a whole. Goodness of fit, we're going to see how well this data fits, or how well the regression fits the data, really. That's the way it's going to go. All right, a lot of the stuff we're going to look at here is, again, going to seem very familiar, right? It's stuff that we kind of talked about in the ANOVA chapter, just applied to something new, right? So instead of using it for the ANOVA, we're using it for the regression. So we want to know how well our data fits, right? And we're going to do essentially what we did in ANOVA. We're going to look at the variances. So we're going to have our total sum of squares, TSS, right? That is equal to the sum of yi minus y bar squared. So this is just the kind of the numerator of a variance calculation, right? So the sum of, usually when we see it, it's x, right? The sum of xi minus x bar squared divided by n, right? That is what that is. So we're just ripping that off. That's giving us the total variation in our dependent variable, right? So how much it all differs from itself. Right, we've already talked about sum of squared errors in the previous video, right? This is just, right, our error is yi, the observed, minus yi hat, the predicted, right, squaring those errors. Right, the new one that we're going to introduce is the sum of squares regression. So our sum of squares regression, we can think of this is analogous to our sum of squares treatment, or our sum of squares blocking that we looked at in the chapter on ANOVA. Right? It's just the variation that is explained by the regression. Right? So with sum of squares treatment, it was the variation explained by the treatment. It was the between group variation, right? The variation that's explained by the data being in those different categories. Here with our regression, it's based on that, right? So how much does the regression explain? How much of that variation is explained by the regression itself? All right, so once we have those, right, that's not the end. We've got one other thing to look at with these. So with this, we're going to calculate, with this information, we're going to calculate something called the coefficient of determination. You don't really need to know that long name for it. It's more commonly referred to as R squared. And it's the notation is it's just a giant R. It's a giant R. It's a capital R, and that's squared. All right. So R squared is equal to the sum of squares regression divided by the total sum of squares. We can also calculate it as 1 minus the sum of squares error divided by the total sum of squares. Right? It's just kind of going to depend on which pieces I give you, really. Right, but in either case, what we are seeing here is a ratio of explained variation to total variation. So how much of the variation in our data is explained by the model? That's what we're getting at. Right? And in fact, that is how we are going to interpret R squared. So R squared is the percentage, or once we get R squared, it's going to be a decimal value. We can convert that into a percentage. And then that percentage is going to be how much of the variation in the dependent variable is explained by the model. All right, let's take a look at this in action. So for our example, our hats and age example, I went ahead and got our sum of squares. So these are our sum of squares. All right, our total sum of squares is 836.5. Our sum of squares error is 559.352. And our sum of squares regression is equal to 277.148. All right, now that we have these, we can go ahead and calculate R squared. It's a pretty simple calculation. All right, we're just going to take our sum of squares regression, which is 277.148. We're going to divide it by the total sum of squares, 836.5, and we are going to get 0.331. All right, that is our r squared. So again, r squared, and I can't believe I didn't write this in my notes. R squared has to be between 0 and 1. So you should always get a decimal value. If you get something that's not in this range, that's going to indicate that you made a mistake. You need to go back and check your work. You might have just put your total sum of squares on top, your sum of squares regression on bottom, or something like that. Punched in the wrong number, but regardless, all right, we should get a number between 0 and 1 from the calculation itself. Right here, we've got an r squared. Again, we've got an r squared of 0.331. All right, so what does that mean for our regression? That means 33.1% of the variation in hats is explained by the model. Right, so also you see here, or for a generic version, just whatever the dependent variable is, right? So whatever the, whatever r squared is, once you put it into that percentage, right, it's that percent of the variation in the dependent variable is explained by the model. Right, for our purposes, it's hats. Now, when we're doing this with our simple linear regression, where we've just got one independent variable, we could also state that, however much, I'll just use this as an example, 33.1% of the variation in hats is explained by age. Right? You could say that the independent variable is explaining that, right? Once we get into multiple regression, we can't do that because there's more than one and you can't really parse out what's doing what. But if we only have one explanatory variable, we only have one independent variable, then all of that explanation, right, is coming from that one variable. All right, so let's talk about confidence intervals. Before we get into talking about confidence intervals for beta 1, I want us to talk about confidence intervals for mu, right, the population mean. Right, it's the first type of confidence intervals that we've looked at. So let's just write that up real quick. All right, so this is what a kind of 100 times 1 minus alpha % confidence interval for mu would look like, right? And this is really the basic format of all confidence intervals. We've got our estimate, right? In this case, x bar. We've got our critical value. Here we're going to use t because I'll just tell you that's what we're going to use for our b's and our betas. Right? And then we've got our standard error, right? So here, this would be sigma divided by the square root of n, or s divided by the square root of n, right? That's that standard error of the sample mean. All right, so we're going to need all three of these variables, or not, they're not really variables, all three of these figures to be able to find our confidence interval. All right, we're going to be looking at a confidence interval for beta 1, so we need the estimate of beta 1. All right, the estimate of beta 1 is B1. So we've already got that. We're going to need a critical value. We're going to use the t distribution. We'll talk about the degrees of freedom and everything like that in just a moment, but that's going to be pretty much standard, right? But we are going to need our standard error. Here is the formula for the standard error for B1. All right, so we've got SE squared, so this is our mean squared error. Well, one, it's under a square root, right? The square root of mean squared error divided by the sum of xi minus x bar squared. All right, so really what we're saying is how much error, what's the mean, what's the average error, and then how spread out is my data. Right? The larger this number is, the smaller that standard error is going to be. The reason for this is kind of the idea is that if you've only got data for a very tight little group, it's not going to give you, there's not going to be as much variation, you're not going to get as much explanatory power. If you've got data that spans a much wider range of values, that's going to give you much better explanatory power. Right? Now don't panic, I'm not going to make you calculate these. One, because they're just very long, they're just very complicated. Most of the time, not most of the time, all the time, in this class you will be given the standard error. One thing to note before we actually start looking at these, looking at the confidence interval itself, just a note on how you might be given that standard error. Right, one, it might just say SB1 equals blank. Another way that it's commonly portrayed is once you've got your estimated regression equation out. So I'm not going to actually write one out, but let's say all right, so that's the generic model. Sometimes underneath that estimated equation, it'll have kind of standard error. It might not say anything, but underneath the actual estimated regression equation, right, there will be little brackets with numbers in them. Right, whatever coefficient it's under, that's the standard error for it. Right, so this would be SB naught, this is the standard error for B naught, SB1 standard error for B1. Now that we have found how to get our standard error for B1, we can actually get our equation for the confidence interval for beta 1 on the board. And this is it. Looks similar to the confidence interval formula that we just looked at for the population mean. Right, we've got our estimate of the parameter, right, B1 being the estimate of beta 1. We've got our critical value, right, we're going to be using t, right, so t alpha divided by 2. Of course, when we're doing a confidence interval or a two-tailed hypothesis test, we need to divide alpha by 2. And we're going to have our degrees of freedom. Our degrees of freedom for this is n-2. The reason it's n-2 is because we are estimating two coefficients or two statistics, right? Similar to our degrees of freedom for the population mean, if we're using t, then it's n-1 because we're only estimating one thing, right? The sample mean. But with regression, we're estimating two things. We are estimating beta 1, right, with B1, and we're also estimating beta naught with B naught. So n-2, and then of course we're going to multiply our critical value by the standard error, SB1. Right, so now let's look at an example. All right, so we're going to calculate a 95% confidence interval for the coefficient associated with age. So we're going to be finding a confidence interval for the B1 that we estimated. So we're going to just set this up. Oh, actually, before we set that up, do need to note that our standard error is equal to 0.691. All right, the rest of it we've already seen, but this one we haven't gotten yet. So let's start filling this up. So we're going to start with our estimate, all right? Our B1, in this case, B1 was equal to negative 1.375. We're going to add and subtract from that the critical value. All right, in this case, we're doing it at the 95% confidence level. That means our alpha is 0.05. So alpha divided by 2 is 0.025. Our degrees of freedom are n minus 2. We know that n is equal to 10, so 10 minus 2 is 8. So that will give us, then we'll include our standard error, which is 0.691. When we go to our chart and we find our critical value, we're going to get a value of 2.306. All right, we're going to multiply that by our standard deviation. And the product of our critical value and our standard deviation is 1.593. This is also the margin of error, of course. All right, so let's give ourselves a little bit more room and continue with this problem. All right, we'll just return to the last step. So negative 1.375 plus or minus 1.593. So at that point we were all but done. The only thing left to do is add and subtract that margin of error from our B1, from our estimate. When we do that, this is our result. So a lower bound of negative 2.968 and an upper bound of 0.219. So a couple of things with this. One, we can interpret this. We can interpret it like any other confidence interval, right? We are 95, or whatever the percentage is. In this case, it's 95. We're 95% confident that the population parameter is between those two numbers, right? Whatever our upper and lower boundary are. All right, specifically for this example, we would say I am 95% confident that beta 1 is between negative 2.968 and 0.218. All right, so that's the straightforward the straightforward interpretation, but there's also something else that we might be interested in. With this, right, with this confidence interval and really any other confidence interval, we can use those to evaluate two-tailed tests. So let's say we want to test the significance of beta 1. So our null hypothesis would be beta 1 equals 0. The alternative is that beta 1 does not equal 0. All right, so let's just take a second to really think about what these mean. So if beta 1, so if the null hypothesis is true, and beta 1 equals 0, that means when we have our equation, I guess really we could just write it in terms of the model. The end results are going to be the same, but still. All right, so yi equals beta naught plus beta 1 xi plus ei, right? If beta 1 does equal 0, then that entire term cancels out. And all we're left with for how we find y, right, it's just the constant plus some error, right? So if beta 1 does equal 0, it means that x, right, doesn't have any effect on y. Doesn't matter what value x is, it could be 1,000,000, it could be 0. It's going to have the exact same effect because you're multiplying that by 0, so you would always get 0 there if beta 1 is equal to 0. All right, so this is really where the tests of significance are important. We looked at the idea of tests of significance when we were in the first and second chapters, right? Or really the first chapter, they weren't that impressive when we were just looking at a single population or at a single mean. They were a little bit more useful in the next chapter when we had two populations we were looking at, so chapter 11. But this is where they really are very popular. They are popular, but they're also very important, right? Because if our independent variables don't have an effect on our dependent variables, then we don't want them in our model, right? And so if the parameter, right, if beta 1 or whatever we're looking at, if it's not significant, then we don't want whatever's attached to it in our model. We need to figure some other things out, right? And of course, if beta 1 does not equal 0, it means that there is some effect, right? Some statistically significant effect, right? So anybody can just look at actually that's not true, right? Because what we're doing is we've just got B1. Beta 1 could be anything. We don't know. We're hoping we have a good estimate, but we're not sure. That's why we're doing these tests, right? But to cut a long story short, all right, we can of course look at our confidence interval to interpret a two-tailed test, right? So 0 is our arbitrary constant. If our arbitrary constant is in our interval, we will fail to reject. If our arbitrary constant is outside of the interval, we will reject the null hypothesis. In this case, 0 falls into our interval, right? It's between a negative and a positive number, right? That's a pretty clear sign that we've got 0 right there in the middle. Not necessarily in the middle, but you guys know what I'm saying. All right, and so that would mean we would fail to reject we can't conclusively say at the 95% level that beta 1 doesn't equal 0, right? It does not prove that beta 1 equals 0, right? That's not the case. We're not proving that. We can't prove that. But it is saying that we're not ruling it out. All right, so now let's look at hypothesis testing. Hypothesis testing is going to be done more or less exactly the way we've been doing it. Really the only thing that's going to be majorly different is something that we saw already just now, right? For the hypotheses, right, so your null and alternative, you're going to be using beta 1 or whatever beta you're looking for, usually beta 1 in this chapter, right? You're going to be using beta 1 equals your arbitrary constant, does not equal to it. You can have your left-tailed, your right-tailed, all of that is exactly the same. Our critical values going to be pretty much done exactly the same the way we saw them on the board. Just a reminder that when we have a one-tailed our alpha is not divided by 2, so if we're doing a right-tailed or a left-tailed test, right, we're not dividing alpha by 2 for our critical value. And of course, when we're doing a two-tailed test, we will be dividing alpha by 2. Right. The degrees of freedom for both of these is the same as it was for our confidence intervals. It is n-2. And we will have the same test statistic for both cases. And again, this is a pretty standard format. Our estimate, subtract our critical value, and then divide by the standard error. And that's basically it. The rejection rules are going to be the same as they are for doing any of the other hypothesis tests we've done, whether that's a hypothesis test on a single population mean or 2 population means, so on and so forth, right? They're still going to be governed by those same rules. All right, so once again, we're going to look at an example. We've got one thing that we've looked at, so we're going to keep using it. So we're going to test beta 1 for significance. All right, in the last example, when we were doing our confidence interval, we've already seen that it's not significant. Well, it's not significant at the 95% level, right? So maybe we want to check one of the other commonly used confidence levels, right? We wouldn't want to do 99% because if it failed, or if we failed to reject at 95, we're going to fail to reject at 99. So we might want to try 90, see if that does anything for us. All right, so we're going to test beta 1 for, that's a weird way of phrasing that, but that's okay. Test beta 1 for significance at the 90% level. So let's go ahead and get started. Of course, we're going to start with our null and alternative hypotheses. So our hypotheses should be relatively easy. One, we know what we're testing, it's beta 1, so that's what needs to go first. And then we know it's a test of significance, that's a two-tailed test with 0 as the arbitrary constant. So we have that. Next, we're going to need to find our critical value, so let's go ahead and sort that out. So this is a two-tailed test, so we're going to be dividing alpha by 2. We're doing it at the 90% confidence level, so that means alpha is equal to 0.10. So when we divide that by 2, we're going to have 0.05. Then of course we'll need our degrees of freedom, which are n-2. N is 10, minus 2 is 8, so that's our degrees of freedom. So we'll go to our chart and we'll see that we have a critical value of 1.860. It's at this point that if we so choose, we might want to go ahead and draw out our distribution, kind of visualize this. So we've got, and then kind of go ahead and place our test statistics, our critical values and mark the rejection regions. So we're going to have 1.860. All right, but this is a two-tailed test, so we need to remember that we don't have one critical value, we actually have two. We have the positive and we have the negative. All right, so we're going to have two rejection regions, one to the right of positive 1.860 and to the left of negative 1.860. So now let's find our test statistic. So when we're doing these tests of significance, the test statistic is pretty easy because our arbitrary constant, what we're subtracting in the numerator, is 0. So we can just kind of leave it out. So all it is B1 divided by the standard error of B1. So negative 1.375 divided by our standard error of 0.691. And that is going to give us negative 1.990. We could either just eyeball it, well, we're not really eyeballing it. We could either just compare our test statistic to our critical value, just looking at the numbers, or we could go to our chart. We can see that negative 1.990 falls to the left of negative 1.860, so it falls into that rejection region. So our result is that we would reject the null hypothesis. All right, we'd also probably want some conclusion. I'm going to just go ahead and tell you, I'm not going to write that down just because there's this is the last thing and there's no space left on there. But for the conclusion, right, we would want to say, one, right, we've rejected our null hypothesis, but we also want to stay what that means. In this context, it's really just we rejected the null hypothesis, so beta 1 is significant, right? That's what H1 is telling us. That's what our alternative hypothesis is telling us. If beta 1 doesn't equal 0, that means it is significant. So our conclusion can be reject the null hypothesis, conclude that beta 1 is statistically significant. All right, that's the end of this chapter. I will see you in the next chapter where we are going to be covering multiple regression. So we're going to add a couple more things to the mix. All right, I'll see you then.